The synthetic wheel was introduced as a conceptual model by Tad McGeer in his 1990 paper on passive dynamic walking. It serves as a very gentle introduction to the dynamics of walking. It involves combining the dynamics of two kinds of pendulums. The first is an inverted pendulum, which means that it swings about its bottom, and the second part is an upright simple pendulum, which swings from the ceiling. The inverted pendulum is going to roll atop an arc-shaped foot, and it's going to have all of its mass concentrated at the hip with an amount of mass capital M. The arc foot has a special feature, which is that its radius is actually going to be equal to the leg length L, and so this is just going to function like a piece of a wheel and roll just like a wheel at constant speed. We're going to measure the angle of the stance leg with an angle Q1, which is going to be defined as positive as measured counterclockwise from the vertical. As for the swing leg, it's a simple pendulum, and I've drawn it hanging from the ceiling for now, and we'll relax that constraint in a little bit. But what's special about the swing leg is that it's a simple pendulum with all of its mass concentrated at the bottom, at the foot. But this mass is very small. In fact, it's infinitesimally small compared to the mass of the pelvis. And so we say little m, the mass of the foot, is much smaller than big M, the mass of the pelvis. This swing leg is going to move freely, and it's like a regular pendulum. And when we release it from the ceiling, we're going to actually attach it to the hip of the inverted pendulum. And that inverted pendulum is actually going to act like a base for the simple pendulum, and that base is going to move at constant speed. The swing leg angle we're going to measure with an angle Q2, which is also defined, measured positive counterclockwise from the vertical. These two pendulums are just stuck one onto the other, and that forms our walking model, which is just going to include the dynamics of both things acting at the same time, where the stance leg moves on a level path for the center of mass, which also makes for a constant speed for the base of the swing leg as a simple pendulum. We can next plot the motion of the inverted pendulum. We're going to make a plot of the angles versus time, and the inverted pendulum is going to be Q1, and since it's just a hub of a wheel, the wheel is going to move at constant speed, and so Q1 is just going to move it's going to be a straight line plot, constant speed, moving from positive to negative, meaning that the inverted pendulum is moving in the clockwise direction as we've defined these angles. Meanwhile, the simple pendulum is attached to that base. A constant speed base doesn't actually affect the motion of the pendulum, just like when you're on an airplane or on a train that's moving at constant speed, that doesn't affect the dynamics of anything that you're doing. You can walk down the aisle of the airplane, and that's no different from walking at the speed of Earth, which in fact is also not zero compared to the speed of the galaxy. So the simple pendulum's motion is going to look like this. This is a little piece of a sinusoid, and we had to choose initial conditions such that the swing leg moves to an equal and opposite angle as the stance leg, and also does so at the same speed, angular speed, as the stance leg. And that just makes it extremely convenient for us to switch the legs. We'll now allow the swing leg to make a very gentle contact with the ground and become the stance leg. And then we're going to lift the stance foot off the ground just by a tiny amount. And so now the roles are switched. the former swing leg becomes the new stance leg. The former stance leg becomes the new swing leg. Moreover, this switch happens with no collision, and that's because both of the pendulums were moving at the same speed. They both have the shape of an arc for their feet, and so this switch is going to occur with no change in the speed of either of the pendulums. They just have to change their behavior. The idea here again is that we have bipedal walking with no collisions. Collisions would be the only energy cost here, since everything is otherwise just swinging like a pendulum. So there's no energy cost to this model. Of course, there are also disadvantages to this model. One is that with the foot arc having radius equal to leg length, the result is that we have big feet. Big feet might not be terribly convenient for a walking model or a robot. Secondly, we have essentially zero swing foot clearance. We have the pelvis or the hip moving on a level horizontal path, and the swing leg also has an arc foot with the same radius. And so essentially we have zero height between the swing foot and ground, and so it's only our somewhat arbitrary decision to switch feet that actually changes the contact conditions. So you might think that a solution to this is to reduce the radius of curvature for the arc foot to something less than leg length. And what that would mean is that we would expect the hip not to move in a straight line anymore, but instead to follow a series of arcs. And each time we have to switch from one arc to the next, it means we need to have a collision between the leg and the ground. And also, since the hip is no longer moving in a horizontal level path, we also expect that the speed is going to be non-constant. And then if the pelvis is moving at non-constant speed, we would expect its dynamics to affect the motion of the swing leg. Nevertheless, what this synthetic wheel is doing is it's showing how the combination of two pendulums could, at least in principle, just resemble the motion of a wheel and give motion that moves in a straight line with a constant speed. And of course, the next step is to relieve some of these constraints and to make the walking motion become less constant and look a little bit more like human walking. This concludes the synthetic wheel model of bipedal walking.